Hi, everybody. If you're ever looking for music for like D&D or something, use Fallout. It's so good. Like the original Fallout. Don't use the new Fallout games. Like they're I mean, it's controversial to say that Fallout 3 and 4 are rubbish, but I really think that they're rubbish. Okay, where were we? It looks like with quiz 14 closing last night, I could finally start grading it, so I'm going to probably do that later today. But there's nothing really due upcoming other than pre-lab for lab number 4. So that's really the only assignment on the agenda. Um, and today we're going to finally finish chapter 14 because there's like 3 slides left. So we're going to do one review problem, and that's basically it. So let's go ahead and get started. So we spent not yesterday. I keep saying yesterday because normally my lectures are 2 days in a row. We spent Monday's lecture talking about buffers and how to solve the Henderson-Hasselbalch equation. And then we talked about how to determine the pH of a titration at any point along the titration. And so on the screen here is our summary of what that is. We ended on this slide right here where we showed the graph of a titration of a weak acid with a strong base. So for this slide, this problem is in the perspective of the weak acid being titrated with a strong base. If we were titrating a weak base with a strong acid, like a lot of this would get flipped around in a way. So like the initial pH would not be the pH of a weak acid, be the weak base. But for a weak acid being titrated with a strong base that we're adding, the initial pH is just a weak acid. So always remember for titration problems to answer the question, what's in the beaker? Because that will tell you which of these steps you are going to calculate. Because if your goal is to figure out the pH, you have to figure out the concentration of H3O+. And each of these problems, with the exception of the middle one's not really a problem. That's just more of a, oh, hey, here the math shakes out. You get this as your answer. You're going to do this all different ways. So you're either going to solve a weak acid problem, you're going to solve a weak base problem, you're going to use just the concentration of hydroxide that is present in there after you have reacted with everything. A lot of these are going to use a before-after table to help you figure out what's in there. In fact, you could just use the before-after table every time with a titration problem to help you visualize what's in the beaker. If you don't like drawing a picture, then writing out the before-after table and saying, oh, there's 0 of this in here, so what happens? That could help you. So I'm going to give you one more problem to do. I'm going to give you 0.1 molar nitrous acid, which is a weak acid. We're going to titrate it with 0.2 molar potassium hydroxide. So I want you to tell me how much KOH is required to finish off the reaction, to get to the equivalence point. And then I want you to tell me the pH after adding 5 milliliters and what the pH is at the half equivalence point. You're going to have to look up the Ka value and the pKa for nitrous acid. If you don't want to do that, I will look it up for you. I just have to find it. Let's see here. What do I not need on this window anymore? We'll get rid of Lentech here. So Ka, or pKa, actually. Nitrous acid. Okay, so according to Google, the pKa of this 3.16. I'm going to go mute for a second so that you can do this problem. And then I'm going to look up in the textbook to see if this is actually the Ka. So I'll be right back. Sorry, I had a window capture up there, so when I opened the textbook, it immediately covered it up with a problem. And interestingly, I found out that according to the textbook, the number that they recommend is 3.34. This is why you always check 2 sources, right? So we'll put that there and go ahead and work on the problem, and I'll see you in a bit. Let's do 1 or 2 more minutes, and we'll go over the answers. All right. Sorry, I hit the space bar, which apparently mutes me if I'm hovered over the microphone. So let's go over here. And I'll just make this a little smaller. There we go. Okay. Pen. I just had the pen. There it is. We don't want to work in green. That's hard to see. There we go. All right, so I have 50 milliliters of 0.100 moles per liter HNO2. And I am titrating with 0.200 mole per liter KOH. All right. So what is the volume required to reach the equilibrium equivalence point? I can't speak apparently. Well, if this is our reaction, I don't know why I wrote water because we're not doing that. So the nitrous acid reacts with the KOH, so I'm going to make H2O and KNO2. And none of this we really care about, right? If I were to do a before and after table here, how many moles of HNO2 would be in my beaker? So I would say, okay, well, that would be M times V is moles, right? So that would be 0.1 moles per liter of nitrous acid times 50 milliliters. And so that would just be 0.005 moles, I believe. So 0.1, 0.05. So that's how many moles of nitrous acid are in our beaker. which makes sense, right? Now, if I wanted to completely titrate that, I would need to add just as many moles of KOH, right? Because then at the end, I would have 0 of this. So when do I hit the equivalence point? Well, it'd be when the total moles of KOH is 0.00500. And since I know that M times V equals moles, and I know what M is 0.2, right? I could rearrange that so that the volume that we need would be however many moles I'm supposed to have divided by the molarity, which would be this many moles of KOH. Let's write that down just to be clear. And then the molarity of the KOH. So how many liters is that? It's probably like 10 milliliters, right? Or 0.05. I don't want to do that math in my head. What am I doing? Divided by 0.2. 25 milliliters. Let's write it as liters first. So that's the volume. Hey, get down from there. Sorry, cat. Hold on. Just a second. No, you're not allowed up there. You're gonna knock my stuff over. Sorry, that was an emergency. My cat was about to tear something off the wall. He might still do it, and I might just have to throw things at him. Hopefully he'll behave. So you might have looked at this number and gotten... Oh, he's doing it again. Sorry, hold on. Okay, sorry about that. So you might look at that number and go, oh, well, that makes sense because the molarity is twice as much for the base as it is for the acid, so it should take half the volume. And indeed, that is actually exactly what happens. Oh my goodness, I just told him to go away, and he's probably going to jump right back up. So if he does, I'm just going to kick him out of the room and close the door. So there's the first problem. All right. We want to find the pH after adding 5 milliliters of potassium hydroxide. Okay, so let's do that. Yeah, we'll just scroll down. All right, so we're going to write the reaction for... let's just write it this way. Because these are the parts that we're going to care about. And we don't care about water. So we know how many moles of HNO2 are in the container. We can just scroll up and look at that. It was 0.00500. And we're going to add 5 milliliters of KOH. So 5 mils of KOH would be... Well, M times V is moles, right? So that would be 0.200 moles per liter times 0.005 liters. So 0.2 times 0.005 equals 0.00100 moles. So that's what we're going to be adding here. That's going to react with our acid, so we'll subtract. And that's going to produce nitrite. I now know why my cat is so obsessed with the window. I think there's another cat outside. I'll deal with that during the break, which is in 20 minutes, so he's going to have to deal with it for a bit. So after this reaction is done, we have that much nitrite in the solution. Sorry, nitrous acid. We'll have this much nitrite. And at this point, the volume will be, well, how many milliliters did we put in there initially? I've forgotten by now. So we have 50 milliliters of nitrous acid, and we've added 5 milliliters of KOH. So our volume would be 55.0 milliliters. But I don't know if I actually need this information. I'm just writing it down to note it. Because I have my weak acid and my weak base, I'm going to just throw those into the HH equation. Because this is in the buffer region. So let's do that. So the HH equation is pH equals pKa plus log of base over acid. Wow, I didn't write any of that. Goodness. And so that's going to be, we said the pKa was 3.34 plus log of, this is the base. I lost a 0 in there. We'll just do that. Over the acid, which was 0.00400. And so when I type all that in, let's do, so 0.001, 0.004. So that's what's in the log. We're going to log that. And we're going to add that to 3.34. And there's our pH. Oops, that should be a 4, the last digit there. There you go. So that's the pH after adding 5 milliliters of KOH. All right. What would the pH be at the half equivalence point? Well, at the half equivalence point, you've reacted exactly half of your stuff. So the pH will equal the pKa, right? So at half equivalence, pH equals pKa, which equals 3.34. And the reason that this works out is that at the halfway point, just as a review, if pH equals pKa plus log of base over acid, at the halfway point, we would have, for this particular problem, since there was 0.005, we'd have 0.0025 left over, or something like that. Maybe not that many zeros. This would be what we have for base over acid, right? We'd have the same amount of both, which is just 1, right? Well, what's log of 1? When we go put this in log, boop, boop. Log of 1 is just 0, right? So pH equals pKa plus 0, or pH equals pKa. So if you have a 50-50 mixture of acid and base in your buffer region, if those amounts are the same, the log of that ratio is going to be 0. And so the pH at that point will equal to pKa. All right, I believe that that's all the problems on that slide. Let's see, are there any more? No, there's not. Okay, cool. So on the quiz for Chapter 15, I'm going to put a problem like that on there. And I'm going to ask you to titrate a solution and tell me the pH initially at some point in the buffer region, some volume that will be the half equivalence point at the end point, and then past the end point. And I could pick any of those or even more of them. Like I could give you after the half equivalence point if I want to. It'd just be another buffer problem. So now, because this is all like review of everything we've done this chapter, it's not difficult per se to do the tasks because you've literally already done these tasks. What's difficult is just getting your head around, okay, which one of these things that I do? And the before and after table is invaluable for that. So just always do a before after table for these titrations to guide you, and you should be well on your way. All right, so we talked about strong base reacting with weak acid. What if we go the other direction? What if we do weak base with strong acid? Well, if we do a weak base, the pH starts really, really high instead, and then it just goes down. And then the reaction curve looks kind of like we have mirrored everything around the equivalence point, more or less. Now, the Henderson-Hasselbalch equation still works for bases. It's just that you have to use the pKa. You cannot use pKb. There is a version of the equation that uses pKb, but since we're measuring pH and not pOH, we want to be using pKa anyway. So the pKa of NH3, for example, so this is the titration of NH3 with HCl. And I know this because, it literally says it right here. I was going to be like, well, I know what the pKa is. It's like 9 or something. But a better tell is it literally says that on the screen. So let's trust that over just like Professor West thinks that's what it is. So when we do this, at the start we're going to have a weak base. And we're going to solve it like a weak base problem. At the end, we would only have the conjugate acid, so we would have a weak acid problem. And then in this region right here, we have a buffer. And we would treat it like a buffer, and we would use the Henderson-Hasselbalch equation. And you do it exactly the same way. It's just that your numbers are going to be greater than 7, as opposed to less than 7. And the reason for that is the pKa is going to be greater than 7. It'll be like 9.2 in this case. Then down here, this region down here is just, I've added excess acid. So you would calculate the pH based on how much excess acid there is divided by the volume to get its molarity. You could calculate its pH. So again, we're doing the exact same thing. We're not going to do a practice problem like this. I'm just showing you what the graph would look like. What happens if I give you an acid that has multiple protons on it? So for instance, if I gave you this acid, or maybe even this acid, what ends up happening is that when you titrate these polyprotic acids, you get multiple equivalence points. This is going to be relevant for lab number 3, which is very ironic that we do this at the very end here. But we don't do any problems for this titration. Instead, I more or less just teach it to you in the laboratory. So we would have done this 2 weeks ago, actually. At this point, this would have been week 4. Instead, we're going to probably do it next week during week 7. But what you're going to do when you titrate a polyprotic acid like this is, for each H plus that is on your acid, so in this case, since there are 2 H's, we would have 2 equivalence points. And your equivalence points are indicated by these inflection points on your curve. So Do we all know what an inflection point is? An inflection point is in calculus where the second derivative goes from positive to negative, but graphically what that looks like is that you have something that is curving up versus curving down. And we know what I mean by curve up, right? So this is curving up. This would be curving down, for example. If it kept curving, it would eventually curve down. And the point at which that changes is the inflection point. The inflection point on this graph is the equivalence point. And in the laboratory, you're going to have to look for that. What we're going to do is we're going to plot the second derivative of your curve. And we'll plot it as a data table. And what you're going to do is you're going to look for the instant that the number turns from a positive number to a negative number. And once it does that, you know you found the equivalence point. And we'll talk more about that when we graph the curve, because I know not everybody is taking calculus. Hopefully by now people have taken what is it, 142A? Maybe it's just 142. Is that calculus? I don't know. I don't know the math numbering system, because we keep renumbering it every, like, 5 years. But that's a very basic premise in calculus. So you cover that in calculus 1, what an inflection point is. So you're going to look for inflection points, and you should have one of them for each h that you have in the solution. Since you know the inflection point, because you can do it graphically, pre-calc is 141 and 142. Okay, so it's probably 151 is calc 1. So I drew my arrow very poorly, but since you know where the inflection points are, you can then calculate the equivalence point, which will tell you the number of moles of base that you added if you didn't have a way to actually determine the number of moles of acid that were in there. Maybe your acid is unknown and you don't know its molar mass, but you could calculate it this way. So for each equivalence point, you're going to add the same volume, because it's going to require the same number of moles of titrant. So if it took you 25 milliliters for the first equivalent, the second one will also take you 25 milliliters. Finally, at the midpoints here, so right here, so at 12.5, this would be pH equals pKa for the first dissociation, and then this would be pKa for the second. Oh my god, I hate this PowerPoint in this tablet. That would be pKa for the second dissociation. So the Henderson-Hasselbalch equation can still be used. And that's really all I can think of that's important about these titration curves. So let me get rid of all this, because a bunch of text is about to appear. That's good enough. Oh, this is H2SO3. Yeah, that makes sense, because it would be a weak acid. I was just writing down the first polyprotic acid I could think of. So what we're going to do in the acid lab, so not this week, because this week's lab number 4, we're doing buffers. Next week we'll do the polyprotic acid. What we're going to do is we're going to give you 3 possible mystery acids. You're going to pick one unknown, and then number 1, number 2, number 3. And you're going to have all sorts of different possibilities you can pick from that are all very similar in name, but have different structures and different pKa's, which you can look up online. Your job will be to identify them, and you could do it by titration alone, but we're going to have you do an IR, which tells you something about the types of bonds in the molecule, because you'll know its structure, because you can look it up. And we're going to have you do NMR, which tells you something about the arrangement of carbon in the molecule. NMR is super cool, which is why I want to do this lab, because if you're going on to organic chemistry, and if you're in 163, there's a good chance you are, because biologists have to take it. you're going to do NMR all the freaking time. And NMR is going to be your best friend. Because NMR will tell you, hey, this is what you have. And you could solve for the structure. And it's super cool. All right. Oh, that was it. Sorry, I didn't realize that was the last slide there. So, this slide is basically just telling you, hey, you're going to do this experiment for one of the labs. Here's the gist of what I just said. So, all right. Yay, hooray, finally! There's no more Chapter 14 to talk about. It's over. I need to update this, because I don't play World of Warcraft anymore. In fact, that picture is probably like 12, 13 years old. So, alright. Your screen will go blank for just a second while I close the Chapter 14 slides forever. Never to be opened again. And then we're going to go to Chapter 15, which, LOL, has like 7 slides. Like, I don't know why they do this. In fact, we're probably going to finish Chapter 15 on Monday. Like, it's just that short. Like, what the heck? Alright, so Chapter 15 is the last of the equilibrium chapters because we've done enough fucking equilibrium problems, right? We're so sick of equilibrium. I never want to draw another ice table. Please get it away from me. I'm speaking for everybody here, I assume. I want to do something different. Well, too bad. We have to do more equilibrium. So, in this section, what we're going to do is we're going to do a special type of equilibrium called the solubility product, which is basically, hey, I have a substance that's insoluble, but nothing's really truly 100% insoluble. There's always a little bit that dissolves. And we're going to calculate the equilibrium constant based on that. And then what we're going to do with all of that is we're basically going to do water quality. So this is the chapter on water quality, which I personally find super interesting because water is very important. And it's important that we don't have shit in our water that would be toxic to plants or to people or to animals. I don't know why I said plants first. I prioritize plants over people. That says something about me. I was a neutral evil druid in a previous life. I don't know. But yeah, so we're going to talk a lot about like, oh, there's lead in this water. How do we get rid of it? We could precipitate it out. Well, if this precipitate is extremely insoluble, can you throw it in the drain safely, even if it contains lead? And the answer to that, surprisingly, sometimes is yes. Believe it or not. So, we're going to answer a whole bunch of questions like that in this chapter. So, we're going to start with that as our starting point. Insoluble does not mean absolutely nothing dissolves or dissociates. Some amount of substance will always dissolve. And so what we're going to do is we're going to write an expression. I'm going to just call this AB. This is going to be some solid, insoluble substance. We're going to allow part of A to dissociate. And then if I was going to write an equilibrium constant for this, that would be equal to products over reactants. But you'll notice that the reactants are a solid, so we don't include them. And so that would simply be this. And the K that we use is solubility product, because it's a product, right? We're just going to multiply the ions together. So this is called KSP, or solubility product. And writing equilibrium expressions for KSP could not be easier. You're always starting with a solid because we're talking about insoluble stuff, right? So you never just write it. So you're only ever going to have a product when you write out your equation for KSP because you're starting with a solid and writing how it dissociates. So that's easy enough. That's way easier than all the weak acid and weak base mumbo jumbo that we were dealing with, right? So let's look at magnesium fluoride and let's write its KSP equation. So here's the reaction. If If I wanted to write KSP for this, I would write magnesium and then fluoride. And I got this 2. What do we do with 2s? You do that. In acids and bases, it's very uncommon to have exponents. But in KSP, we're going to have exponents all the time. So we got to remember it. Don't forget that step. I know it's been a while since Chapter 13 where we actually put exponents from coefficients in our equation. That's going to be the part that we mix up. All right. So there's our equation. Let's do some equilibrium problems with this and try and solve for a concentration of something. Oh, first, though, where do you look up KSPs? They're in Appendix J in your textbook. So I actually have Appendix H open. I'll just click over to J. And we'll show you how tiny these numbers are. So that should capture. That's kind of small, but that'll be okay. So here are some KSPs for just various numbers, and you're going to see that these are going to be like 10 to the minus 10 or lower. So like there's a bismuth compound right here, 10 to the minus 97. Like, holy shit, that's really, really insoluble, right? Now keep in mind, this is going to be something squared times something cubed. So we're going to get a giant number for our exponent just because I don't want to highlight OpenStax, that's fine. There are so many ions. So the more ions something has, the lower its KSP is going to be just by virtue of how math works. But we're going to show some consequences of that later and why we can't always just rely on these numbers to compare stuff directly. So for instance, if I asked you, what's more insoluble, PBS or PB3PO42? And you would say, oh, well, look at this giant number that it makes. This must be more insoluble. Where in reality, I think it's this one, because I only have lead multiplied by sulfide versus I have something cubed times something squared here, and I get not minus 54. So it's hard to compare these unless they dissociate into the same number of ions. So we'll talk a little bit more about that later. But when you're looking at KSPs, don't immediately just jump to, oh, it's a smaller number, it must be less soluble, because that might not be the whole story. What does tell us the whole story is this. The molar solubility of a substance is referred to as S. That's the variable we use. And it's basically, what's the concentration of your ions in moles per liter? And the way that you're going to solve that is we're going to make another ice table. I know. Frickin' ice tables again, right? And we're going to do something like this. So if I do the magnesium fluoride one, you know, it might just be because I put my hand on the tablet and it's reading that. Even though I have that disabled, it shouldn't do that. So what we're going to do here is I'm going to go ICE. And initially, I don't have any of this. And this is a solid, so we don't care about it. But when I allow some of it to dissolve, I will dissolve S of it. Now, the only thing I don't really like about the S variable is that it looks kind of like the number 5 if you're writing really quickly. So now, I made one S of this one, but here I have a 2, so I got to put this 2 here. And so our solubility product would be S and 2S, and we would say, okay, well, KSP equals S times 2S squared. And then we could solve for S, and S would tell us how much dissolved in there, based on whatever KSP is. So, in my opinion, doing KSP problems is way easier than what we were doing before, because one, we know that S is going to be small, so we can make the S as small approach. where it was X's small approach, because KSP is just this stupidly tiny number. And 2, see step 1, I guess? I don't know. I really only had one step there. We've done this before, so it's not very difficult, is where I'm trying to go with this. So let's do an example. What is the molar solubility of silver chloride in water? And then here's KSP. Oh man, this looks like chapter 14 stuff. Let's just get rid of that forever. Goodbye. I mean, not technically forever, but... Now, there is the potential to make mistakes here by not dissociating your ionic compound into the correct substances. So you have to be kind of mindful of that. Make sure that you know what ions form for things. So you might have to go look up your polyatomic ions, or look at the octet rule, or whatever. So we're going to dissociate this. So initially, there are none of these ions in here because it was just pure water. This is a solid, so we get rid of it. And when this dissociates, I will produce S of our silver ion and S of our chloride ion. So at equilibrium, we will have a concentration equal to whatever S times S is, and that should equal KSP, right? So the square root of KSP should just be our S, which would equal... So if KSP was 1.77 times 10 to the minus 10, and then we square root that, that would be the concentration of each of the ions in our solution. And they have to be equal. Like, they can't be different. There's no way they would be different, because for every one of these I make one of these too. So they have to be the same. So by dropping a chunk of silver chloride into water, only this much is going to dissolve. 1.33 times 10 to the minus 5 moles per liter. So essentially nothing, yeah? And that's all there is to it. That's basically what we're going to be doing this whole chapter, is just permutations of that. All right. We're going to do this example. I want you to try it, but we are due for a break. So what I'm going to do is say, let's take our break here. I need to get more water anyway. Make sure I figure out what the cat is doing in the window. He left, but who knows when he'll be back. All right, I'm going to start the timer. We'll get the music going, and in 10 minutes, we will return and continue. So see you in a bit. Hi everybody, we're back. So on the screen here, I have iron 2 hydroxide, and what I want you to do is first write the reaction for its dissociation, and then calculate the molar solubility S. So I'm going to refer to it as molar solubility, but always just remember whenever I say this, that you're looking for S. So I want you to solve for S. Tell me what S is for iron 2 hydroxide. If this is its KSP, 4.87 times 10 to the minus 17. Now, you might be able to make a prediction about how big S is going to be based on KSP, but be very careful about that, because don't forget any squared terms. There might be some 2's in there, etc. So go ahead and set up the equation for this, and we'll go over the answer in about 3 minutes. One more minute, we'll go over the answer. All right, let's go over the answer now that my video is done dropping frames here. So, well, I didn't click over there. I got to do that first. All right, so let's write the. Oh, hi! There's a cat right in my ear. So let's first write the dissociation for iron 2 hydroxide. So we would dissociate into iron 2, and then we've got our 2 hydroxides here. So when we make our ice table, don't care about that. It's a solid. We got nothing to start here for either of them. But I'm going to create S iron 2+. I'm going to make 2S of hydroxide. So KSP must be equal to S times 2S quantity squared. And yes, you do square the 2S, not just the S, because we've made 2S of this, and for KSP, we apply this 2 right here, right? So that is not a typo, I guess we'll say. So be very careful about that, because you do want to square your 2S quantity. In fact, whenever we are doing KSPs, you're always going to square a 2S quantity, because the only way you can get 2S is if you had 2 of it, right? So when I multiply S times 2S squared, so this becomes 4 times S squared, because I have to square both the 2 and the S, which equals 4S cubed. So to solve for S, I would then say KSP over 4 cubed rooted is S. Now, how the heck do you do that on your calculator? Not everybody has a cubed root button. And we're going to have like 4th root buttons and stuff like that. And so the way that you do this is, so first let's compute everything that's in the parentheses. So KSP was 4.87 times 10 to the minus 17. We're going to divide by 4. And then we're going to go to the power of 1 divided by whatever root we're going to do. So in this case, we're doing a cubed root. So we're going to raise it to the power of 1/3. And then we'll hit enter. And I get 2.300. Wrong end of the pen. 2.3. How many sig figs do I get? I get 3 here. Times 10 to the minus 6 moles per liter. So that's what S is. So I would plug that back in here for where S is to figure out how much iron I had. And then I'd multiply it by 2 to get how much hydroxide. There you go. So the trick here really is going to be dealing with cubed roots and 4th roots and 5th roots and stuff like that. And remember that you can use the 1 to the... Sorry, not the 1 to the X to the Y button on your calculator. Or maybe you have like a caret button on your calculator, and then you can just type parentheses 1 over whatever your root is. All right. For this one, I have S already figured out. So here's what S is. What is KSP for this equation? Or not for this equation, but for this reaction. So this shouldn't be difficult to do, right? Because if we write out our ice table, it'll look like this. And then what we can do is we'll cross this one out because we don't care. We'll form 2S of our silver. We'll form S of our sulfate. And then KSP must just be 2S squared times S. Or this again, right? You're going to notice that you're going to get a lot of the same equations with S in it for this chapter, and that's normal. It's totally intended. All right, well, if S is 1.2 times 10 to the minus 5, that would be 4 times 1.2 times 10 to the minus 5 cubed. So order of operations, we got to do exponents first. 1.2 times 10 to the minus 5 to the power of 3 times 4. That's totally worthless to me. That's better. 6.912 times 10 to the minus 15. So if you know what S is, you can very easily determine KSP by writing out the ice table. And if we go look this up for... I've already forgotten what substance this was. Silver 1 sulfate? I mean, silver is always silver 1, but... Ag2SO4... That's weird. Okay. I apparently when I made this problem, I copied the KSP and I just called it S. So, because my number in the back of the textbook is 1.2 times 10 to the minus 5, which is total bull. But anyway, for this problem, if that was what S was, Ag2SO4 would be, or KSP, or if that was what S was for Ag2SO4, KSP would be this number. So we did the problem correctly. It's just I used the wrong number to do the problem, or to create the problem, I should say. Okay, so how many of these do I have? There we go. So I have 2 problems for you. You can do the first problem to solve for S, and then the second problem I want you to tell me what KSP is. So I've given you all the numbers that are relevant for these problems, so you don't have to look anything up. But go ahead and do these, and we'll go over the answers in about 6 minutes or so. Yeah, let's say 6 minutes. So see you in a bit. 1 or 2 more minutes, and we'll go over the answer. All right, let's go over the answers. So we'll go over here. That's the first problem. Okay, cool. I'll just hit this button over and over. There. So here's our silver chromate. And it's going to dissociate into 2 silver 1 ions and our chromate. So we'll set up our ice table. So we don't start with anything, but we do produce 2S and S of our silver and our chromate respectively. So there's our equation for KSP. It's going to be 2S quantity squared times S. So all that makes 4S cubed. That's KSP. So KSP over 4 cubed rooted will be our S, which should be, so KSP was 1.12 times 10 to the minus 12, which we will then divide by 4, and we will then cubed root. And I get 6.5 times 10 to the minus 5. I got another sig fig, actually. 6.54 times 10 to the minus 5. So that's how much chromate you have in the solution, and then the amount of silver would be just that times 2. All right, for problem 2, what is the KSP for silver bromide? Silver bromide is used in photography. So knowing its solubility product is rather important because you don't want silver chloride or silver bromide to remain on photographic paper. It's light sensitive. And once you've developed your picture, you don't want any more light-sensitive compound because otherwise everything will just turn black eventually. So we need to dissolve it off the paper somehow. And so that's what photographic fixer is for. And we'll do a problem like that later, I think, actually. So silver bromide will dissolve into silver and bromide. So I got nothing to start. I'm going to produce S of each. And so KSP would be just S squared. So square root of KSP would be S. Oh, wait, hold on. That's not what we want. We want to just solve for KSP. Because I gave you S. So that's going to be 7.3 times 10 to the minus 7 squared. And so that will be our KSP. Oh, there we go. There you go. All right, should be no problem. This is the easy stuff for this chapter. It gets ridiculously awful pretty quickly. All right, let's talk a little bit more about KSP. So I said earlier that we cannot compare KSPs directly because S might be squared or cubed or whatever, and that gives us KSP. So looking at different KSPs here, it's hard to relate them directly. So for instance, the top one has a smaller KSP, but its solubility value S is bigger. So even though this is a smaller number, you don't want to look at KSP. You want to instead look at S. S tells you more or less soluble. So don't look at KSPs. KSPs are just the product of your solubility product constants, however your solubilities, molar solubilities work out. So whether they're squared or cubed or whatever. And it's very difficult to predict that without actually sitting out and doing the ice equation. Or having done like tens of these, you can start to get an idea of like, oh, okay, I have 3 ions. I'm probably going to end with a 4s cubed. That sort of situation. Is there a PKSB? There is. I don't think that we're going to use it in this class. Mostly because, like, it's not super helpful to relate KSPs to each other. Like, for acids, they all dissociate into 1H plus and your anion, so they can be directly related. Like, oh, a lower pKa means it's more acidic than a higher pKa. But for KSP, getting a KSP of 13 versus 11 doesn't really tell us tons, because it's the solubility, the molar solubility that we care about. Now, is there a P solubility? And the answer to that is, actually, there is, but it's done on an element-by-element basis. So if you have, like, a wide range of values for, like, calcium solubility, you could take the P calcium of something. That is a thing that is done. All right. So again, the number of ions is going to affect the result that you get for KSP. A smaller KSP could be because of more ions, or it could be because of really low solubility. It's kind of impossible to tell. Now, if you don't have the solubility available, and all you have are KSPs, you can compare them if they have the same number of ions. I'd sneeze there, sorry. So because each of these splits into 3 ions, they're all going to undergo the same mathematical treatment. with my calculation to get from S to KSP. So they'll all end up in 4s cubed. And KSP has been calculated to do that mathematical process already. So if I have the same number of ions, I can look at either S or KSP. And as you can see here, the KSP that's smaller is indeed the one that is less soluble, because the solubility S for it is a smaller number. So for magnesium hydroxide, KSP is 10 to the minus 13, and the solubility S is 10 to the minus 5. So it's less soluble than the other one, which has KSP 10 to the minus 10 and solubility 10 to the minus 4. All right. So let's talk about situations where we can exploit the knowledge of KSP. What we're generally going to be doing with KSP is we are either going to try to precipitate something out, like by adding stuff to another substance to make a precipitate, or we're going to try to make a mixture such that no precipitate forms. So our goal is going to depend on like what our objective is for a problem. And then we're going to act appropriately. Oh, I do want to precipitate. Okay, I need to get the solubility product to be larger than what KSP is. Or what I should say is I need to get Q to be greater than KSP, because then it'll precipitate. It'll force back towards reactants. If I want stuff to always be soluble, then I got to make Q less than KSP, and I got to keep it under that. If I go above it, stuff will precipitate. So we're going to do both of these things. So we all remember the reaction quotient Q. We did that in chapter 13. Remember that Q is literally just Q is equal to whatever your calculation result is for K whenever you're not at equilibrium. In other words, if you don't know if you're at equilibrium, what you're calculating is Q. For instance, I could just throw in some random concentrations of ions. I have 10 to the minus 3 chloride and 10 to the minus 8 silver. Will a precipitate form? I don't know. Let's see what it multiplies together to do. And if you get a number greater than or less than KSP, first of all, that number that you got was Q, and then you can act accordingly based on your result. So we're going to find whether precipitates form. And for a precipitate to form, the Q that we calculate must be larger than KSP. If Q is too large, then we drive the reaction back towards reactants. Well, look what's on the reactant side. It's a solid. We'll make a precipitate. So that's our goal. Now, if Q is less than KSP, then what the reaction will do is it'll act as if, oh, there's not enough products in the solution. I'm going to move towards the right. And if that's the case, your reaction will try to dissolve more things. You know, unless there aren't any things to dissolve there. In which case, at the given concentrations, if Q is less than KSP, you can never make a solid. And so that might be desirable too. If we want something to dissolve, we'll just make Q really small. We'll just fill it with reactants. All right. This slide basically says what we just talked about from the perspective of saturated versus unsaturated versus supersaturated. If Q is less than KSP, then the solution's unsaturated. Everything dissolves. There's no precipitate. If Q is greater than KSP, the solution is supersaturated. A precipitate will form. And if Q equals KSP, you won't actually see a precipitate, but you are at the maximum amount of soluble ions that you can hold. And if you put in any solid, it will not dissolve. All right, let's do some examples with this. I have lead nitrate, and I'm going to mix it with sodium bromide. Will I make a precipitate? Now, you'll notice that I did not give you KSPs for this, so how the heck do you know what precipitate will form? Well, we're going to play what's in the beaker again. So I need, like, my game show music for what's in the beaker. All right. So let's draw a beaker. And I'm going to add lead nitrate, which means that I'm going to have this in my solution and nitrate. And I'm going to add NaBr, which means I'm going to add this in my solution and this in my solution. Now, obviously, I could just pair these things together with what they started with. So these are all possible substances that will form. I will never form a substance between the two metal cations, so I'm not going to make PbNa. That's not a thing that'll happen. They're both positive. They won't make an ionic compound. But I could form the opposites, right? So I could do this one, which would be NaNO3, and PbBr2. So those are the 4 possible compounds that could form. Now, if we look up the solubility table, you would find out that lead nitrate is soluble because all nitrates are soluble. So is sodium nitrate. And the solubility table is from 162, I believe, or maybe even 161. And then we would learn that all sodium-containing compounds are soluble. So this is probably going to be the precipitate that forms if a precipitate were indeed to form. How do you find that out? Well, what we'll do is we'll go over to Appendix J in our textbook. And that's a little tiny. So we're in Appendix J here. And Appendix J has a bunch of... I don't know where to put this. We'll just put it over here. It has a bunch of substances listed by element. And you can see I was looking up silver here. So I want to look up lead. So here's lead, and I want PbBr2. So it's listed, and it has a KSP. So we know that PbBr2 is insoluble, and here's its KSP. So that's cool. So I'm going to write that down in our notes right here. So KSP is, I can't see it. I got to find it again. 4.6 times 10 to the minus 6. So if we have the concentration of lead and bromide, and we multiply all the numbers together and square and do whatever it is what we have to calculate KSP, and it ends up being this number or greater, then the reaction will be driven back to the left in a precipitation form. So let's write all that out and let's see what happens. So first, let's write the solubility expression. So that would be this. And then we would say, okay, we'll make our ice table. Get rid of that guy. And we would say, okay, KSP would equal whatever S is times whatever 2S is squared. Well, instead of S, what we're going to plug in are the amounts that we have, right? So I have... So this is our Pb2+. And this would be our Br minus. Now, importantly, this replaces this whole thing. And whatever number we have here is going to replace this whole thing too. So we're not going to multiply it by 2, but we are going to square it. So what's our concentration of lead? So that would be 0.0150 moles per liter. And then bromide would be 0.0350 moles per liter. So that's going to equal this. Now, the reason that we aren't doubling it here is because we didn't actually dissociate into 2 pieces. I just added a bunch of bromide in there, so it's already been accounted for. But in order to calculate KSP, we do have to square this. And so what I get is... Oh, you know what I should have done? I should have done the 0.350 first. Let's do that. And then I don't have to do calculator gymnastics here. And I get 1.8 times 10 to the... So this is going to be Q here. 10 to the minus 5. All right. We said that KSP was... I've already forgotten the number. 4.6 times 10 to the minus 6. And so we'll compare these. Well, Q is bigger than KSP. And so what we would conclude is that, oh, we have too many products. The reaction will shift towards the left. So a precipitate would form. And so if I had these concentrations of lead nitrate and sodium bromide and I poured them in a container, I would immediately make lead bromide. And you would see it cloud out. I don't know what color it is. Let me look it up real quick. PBBr2. I want to say that it's brown. I know lead iodide is yellow. Yeah, it's kind of like orangey brown. Is my best guess. Oh, actually, no, it looks like it's white. Okay, interesting. Lead 2 iodide is super yellow, so that's why I suspected that. All right. I need to click over here. There we go. All right, let's do another one of these. Will a precipitate form if I give you these concentrations? Now, it's still lead bromide. So this should be pretty straightforward because you've already done all the work for this problem. But I want you to tell me, will these concentrations produce a precipitate? Yes or no? I'm going to give you 2.5, 3 minutes to do that. We'll go over the answer in just a second. One more minute, we'll go over the answer. All right, so if we go back over to our expression over here, all I really have to do is I just have to scrub these old numbers out that we just did, which would be these up here too. And we'll calculate the new numbers and we'll compare it to KSP. So we've got 0.0600 moles per liter for lead and 0.0150 moles per liter for that. So if I do this, we get 0.0150 squared times 0.0600. There you go. Oops, that didn't actually write. Hold on. My pen is being stupid. And look at that, it's still greater than KSP. So this also forms a solution. Now, what would not form a solution? Well, if I did this, so if I were to do this change right here, then this becomes like that, and then this would become a 6. And now, oh, it's less than KSP. So if I had made this change, actually, you know what? Hold on. We'll just do it this way. So would not form. So if I made this little change here by diluting this by a factor of 10, then this happens, and then this happens. So if you're trying to, like, control this process, there's actually a remarkable amount that you can do here. And what we're going to do when we come back on Monday next week, since today's Wednesday, I guess, right? Yeah, it is. What we're going to do when we come back on Monday next week is we're going to try and precipitate out certain things to separate them. Because if I have a mixture of a bunch of dissolved ions, it's very hard to filter those independently in many circumstances. So if I have like calcium and magnesium, I could filter them both out and trap them in the filter. But what if I want to separate them? Like I want to get all the calcium in one bottle and all the magnesium in the other. How do I do that? Well, I could precipitate them as hydroxides, for example, and they have different KSPs, so one will precipitate before the other. So as long as we add enough hydroxide by changing the number that we have in the equation, which would be, for example, this number, if I slowly increase this, eventually I will get to the point where I have Q is greater than KSP for one, but is less than KSP for the other. And the result will be one of the things precipitates, and so I just put that much hydroxide in, precipitate one of them out, remove it by hand. I have separated the two things. So that's where we're going to go with this next week. So look forward to that, I guess. I don't know. Do people actually like look forward to like, ooh, we're gonna learn something neat next week that's practical? I mean, I guess if you're into water quality, like some of us are, I certainly think it's interesting. Then yeah, be excited. But if you're normal like like most people, nobody cares, right? All right, that's all I got. So on Friday, we're going to do lab number 4. Make sure you do the pre-lab. It is due at 9 a.m. before the lab. And bring the correct lab to the experiment, and we'll play with some buffers. See you then.